So as this is the last session, we're going to present a technique, an estimation algorithm for dynamic models that originated in engineering. So it didn't permeate to statistics until, much later. So originated in engineering among control engineers in the 1960s, was developed by an engineer, Rudolf Kalman. I think was working just to figure out a way to solve efficiently what is called the filter problem, and I'm gonna talk about a little bit. And so my idea is to create and give you an intuition what the Kalman filter is, what it is its use, and then Dr. Tuile is going to follow up with some hands-on applications or examples, right? So first, let's start with a state space model. So we talked about yesterday time series models, and how there were two different ways in which we can approach time series models. Look at the data one, and then try to extract from the data, from past values of the data, some regularities like seasonality and trend, shocks, and so on, that are consistent, and we can repeat it in the future. So we don't know why this happened, but we know that they are consistent, and then we think that we can project that into the future. Now, the other type of analysis of time series or time series data is what we call structural models. Sometimes they are called state space model. And it's when you have an explanation about why you have variables and connectivity among variables in your model that they help you explain what you see, right? So what we now then we can develop much more sophisticated models than the Box-Jenkins, for example, that we did yesterday, that we saw yesterday, in which we have your theory and applied to the projection or the development of the model. So usually when we talk about time series structural model or state space model, mostly we are usually talking about linear models. It can be non-linear, but a true state space representation, it will be more powerful, or it is much more useful if we represent that in a linearized or linear model. And the dynamics as so why the system is here and then change, right, that we saw in this afternoon when we talk about compartment model, is organized, is described by a series of either first order differential equations or difference equations. So we say the future time t+1 is the present plus change, and that change is one step change. So it follows the Markov condition, that the property that everything that we need to know about a system is actually encapsulated in a group of variables, the minimum group of variables that we call a state variables. So, and we are using that's a state variable to describe the system. And then usually we represent the state space model with in matrix notation. These are matrices because we can usually the state variables in a model they are multiple, and what we are saying here is that the vector of the state variables at time t plus 1 is the vector of the state variables at time t multiplied by a matrix of constant or parameters, right? And this can be the differentiation or the derivative um, of xt, or that's in continuous time. In discrete time, you put t plus 1, so one step ahead. And then this is a matrix of, this is a vector of inputs. So how do you control? You want to control the system. And that's where you put, your taxes or cleaner laws or stuff like that, that will affect the state variables. Okay, so sorry about that. So the sometimes, and a lot of the times, you don't observe these state variables. So what you observe is this, what we call the observation, the output variables. The output variables of the system, and the output variables of the system are a linear combination of the state variables. So the idea is what you hope is that if you observe this y of t, or the vector of outputs, there should be somewhat in one-to-one correspondence with linear with these state variables, right? So the point is that if I know this output, somehow I should be able to reach the and know the state of the system. This is what we call that the system is observable. And some other in other disciplines, they will say, well, the system is identifiable because we can see the output can lead us to those hidden variables somehow, if we know the one-way trajectory, right? So then this matrix here is how the inputs sometimes at time t affect directly the output. That's mostly work in a static system, because most of the time what we call dynamic system is this effect that the state is a product of past inputs. So x w sub t affected the state as also u of t minus 1, u of t minus 2, and so on, right? So this is a dynamic representation of the model, and this is and there's a process matrix or a state transition matrix. There are different names for that depending on the discipline that you go, but this is a standard representation of system. So we can think about this representation as a hidden Markov chain. These are the state variables, right? And the states are follow the Markov process. So the idea is that they just depend, the state at time t only depend on the state at t minus 1. And you can forget all the previous steps, and then there's there is observations or output of the system that you observe and those observations, um, uh, those observations will allow you to estimate or to actually get more precise the state of your system, so you can do better projections, or you can refine what the projections, exactly the projections of the system, and so on. So that's what uh, takes me to what is the filter problem. So you have, suppose that you have a linear system like that, the hidden Markov, change, and the system produce an output, and you use that output as a forecast for the future, and then that's what you use your system. You forecast one step ahead, and then you get the real observation, from that you are anticipating, and then there's different from what you projected, right? And then what you say is, um, what am I going to believe? I know my system is not perfect, but the data has a lot of noise. So how I can, make this that's inference better. And what you what usually the filter problem is how to combine these two observations and take and filter out the noise as much as we can. And for that, what we do is a weighted average, right? A weighted average of the what we projected versus what we see, and depending on how much weight you assign to the observations, then your projections are going to ignore. If you assign much more weight to the observations than to the projections, then the system is going to be, your projections are very volatile, right? So it's going to follow all the noise of the in the system. But if your um, um, weight to the observation is very small, so the system is going to be pretty stable. And so what's the best possible weight that you can find? Well, the best possible weight is dynamic, right? It doesn't have to be one weight for all the trajectory of the of the system, of the observation, and it depends on uh, how your observation and how the states transition. So the depend there's some input that you need to know, for example, what is the noise in your observation, what is the noise on your on your model. So what is the uncertainty of your model, what is the noise on the observation, and with those parameters you start adjusting that weight. So that's a filter, right? And what the Kalman filter does is that it gets that weight optimally. So it computes the weight in such a way that the estimator that you get from combining the projections versus what you see, that combination of the state, that estimator has minimum variance, or in general, the minimum um, um, uh, error, mean square error. Okay, so um, this definition I got from this publication, and I think it's intuitive. The Kalman filter is an efficient optimal estimator. When they say efficient, it's not efficient in the statistical sense of minimum variance. This is what they mean by minimum variance here, optimal estimator. But efficient in this case is that compact, is computationally easy to handle because it's a recursive one. Doesn't need a lot of computation. That provides a recursive computational methodology for estimating the state of the discrete data control process from measurements that are typically noisy while providing an estimate of the uncertainty of the estimate. Okay. The dynamic system is linear, and so for ideal condition, the dynamic system is linear, and the state variables form a hidden Markov chain, as I showed you before. The observations are linear combination of the state variables, and because of the hidden Markov chain condition, the estimates of the current state variables are independent of everything else, because they just depend on the previous state, and so conditional on having the previous state, right? They are independent from the previous state variable. So because they are conditional on a state at time t-1, they are not correlated with the state t-1 because that's a constant for that. And then and therefore they are independent of the observation that you see at time t, right? So if errors are normally distributed, then the Kalman filter is an optimal estimator in the mean square error sense of the system state. If the errors are not normally distributed, or for some reason they estimated the noise in your measurements, then at least it's the best linear estimator. So out of all the linear estimator is the one that produces the best the minimum variance or minimum mean square error. Okay, so I just wanted to use a very, very, very simplistic Kalman filter and derive from an univariate state model. So just one variable. I just want to try to derive the equations of the Kalman filter. And so you see that they are intuitive, and what you see in applications of multiple variables and a lot of observation is just a generalization of what we are gonna see now. So suppose that we have this is my nomenclature. So y of t is the observation at time t. I'm not going to distinguish observations from a state. I'm going to pretend that all the states are visible. So they are not hidden in this case. So it's not a big. It's not a problem in the interpretation. So so we have that observation, and then this is the estimate. This is the prediction of y of t at time of y of t with all the data up to time t-1. So all the observation up to time t-1, all the state variables up to data up to t-1, right? So then this is going to be the estimate of y of t, but with data up to time t. That means includes the most recent observation. So this is what I want to optimize here, right? So I have a projection for from period t-1 to period t. Then I observe y of t, and then I need to produce, and I'm going to produce this optimal estimator of the state. I'm going to filter the noise between the two. And how I'm going to do it? I'm going to do it by weighting these two differently to produce a minimum variance estimator. So this is the variance of y t-1 at time t, and this is the variance of the estimator of the observation at time t with data up to time t, and this is what I'm going to try to make as small as possible. And this one is the variance of the observations that you probably can measure that, or figure out from your survey what is the variance or uncertainty in the measurement that you take to incorporate in this cycle. Okay, so if you take a look here, this is what we are trying to do: minimize this variance here, right? And we had this number will become this parameter for next period, right? So that's, we are just moving one time ahead. So um, as I told you, we are going to find k. That depends, different depending on the time, and this weight is going to weight the observations versus the projection of the system, right? And with the deterministic factor derived to minimize the variance, right, of this estimator here. And then uh, what I've done here is, if I want to minimize the variance of this, then this is the filter that produces this one. So I'm going to simply just find out that variance, derive the variance, and I'm going to try to minimize it as a function of k. So you remember from the basic stats, if you the variance of a constant times a random variable is the constant squared times the variance of the random variable, and so on and so forth. So the computation of the variance become this one. And then I take derivatives with respect to k and make that equal to 0, just to get for minimization conditions, right? And once I do that, then I solve for k. And after some simple manipulation here, I found that the k of t, which is what we call the Kalman gain, that weight that I assign to the most recent vector of observation, is simply the variance that of the estimator from last period, okay, divided by the same variance plus the variance of the observation. And that's depending these variance of the observations, usually is constant. It doesn't change with t, and or it can, but usually it's how we take that measure, and is pretty much set. These numbers here, the variance of the estimator of the variance of the projection, they're going to be changing in time, and they're going to be changing in time because we have equations that that follow some dynamics, one, and your estimator is changing all the time. So the variance of your estimator, so the estimator is changing all the time because previous values of k, and therefore it is either getting more stable or less stable, and depending on that, then the Kalman filter will produce different results. So finally, with this formulation, what we are doing in Kalman filtering is the following. So I want to estimate the state of the system time t after I collect my last observation, or the last vector of observations. And then what I'm going to do is I'm going to take what I projected for this period, plus I'm going to get a correction to what I projected for this period. And this is the correction, the correction factor, what I see minus what I projected. And then I'm going to multiply that correction by a Kalman gain. This is this parameter. And this is how much the Kalman filter is gaining, is actually increasing the or decreasing, right? The adjusting the projection that I made. Okay, so this is first I predict and then I correct. Okay. So we could go and do exactly the same, kind of derivation to produce how to actually update this the variance of the estimator of time t with the data up to time t, because we are going to use that to project the future the future state. But I just didn't want to go into more computation, but this is actually the one important result that you see is very easy to derive. And in matrix notation is pretty much the same thing, but it just use matrix algebra or linear algebra in order to get that. So so in terms of the Kalman filter, this is how the Kalman filter works. So you have an initial state of the system, so you have to measure or guess what the initial state is, and then with the initial state, then you make a prediction for next period, and then your system, you have to wait until the next period, until you collect the data, the measurement, and then with what you projected and the data collected, you update, you filter with the Kalman gain, and then produce the estimate of uncertainty, right? The state estimate, that's what we saw here, and also the estimate of uncertainty, which we didn't derive the formula, but it's we can do that in a similar way, and here, and then the process repeats with this information. Then you update, and then you predict, and then you collect another information, and so on and so forth. So that's how it works. It's just a recursive filter that only uses the state, the information from the previous state to to forecast the future. One thing is important to realize is that at this point, when I'm taking when I'm taking the variance of this of this estimator, I took the variance of this part plus the variance of this part, and I can do only that if these two variables are independent. And so that's the important thing of the Markov chain assumption, that conditionally on the current state, all the information is the observation at time t is independent of everything else. So if I didn't have that, then it would be a problem. So this is a an example of one performance of a Kalman filter, right? So we are here trying to measure a constant state. So we're trying to guess, let's say, the height of a building, right? And then we are, using observations, the measurements of the height of, and those measurements are volatile, right? And so with the information that we have about the accuracy of the uncertainty of this measure, then we started with the projections, with the estimate, right? And so we predict, and then we correct, and we correct. So we get the information, and then we correct. We get the new information, and then we correct, and so on. So after a few iterations of the filter, you see how the Kalman filter is converging pretty rapidly to this unobserved true value of the system. That's the green line. And you see how much volatile are those the observations, but with the proper gain, this estimator, is have minimum variance, right? And minimize the mean square error. So you see how efficient it is, and that after a few observations, it just converges directly to the true value. And what can we do with this is, we can do a lot of applications with survey data. And suppose that we want to, we get measurements from surveys, and we want to know what is the true state, and in order to forecast the future state. So this is a tremendous uh, uh, tool to create on the fly better estimates of what you see, and then put that, recalibrate your model, let's say, with the state variables, and keep going. For example, the ones that we are using up to now, the models that we're using up to now, we simply have the original parameters, and then we take the observation of the data as as the truth, and pretty much we do some um, uh, estimates of uncertainty after a while, and say, well, this is the uncertainty of my projections, given that I didn't modify my model. My model is not recalibrated. My model is calibrated at time 1, and it's not recalibrated until I finish with my observations, my operations, and they can differ. Drastically. But with this technique, what we're talking is that you get a projection of your state. Say I project prevalence, so then I observe the prevalence from NHIS, and I can just filter immediately, right, and update all my state variables. So it's recalibrate optimally at every single point in time. So there's a lot of applications that we can think of, that in tobacco control, for example, in the tracking of an epidemic, for example, and get the best estimate at any point. With it combines the new information, which is this one. Okay. This combines optimally this new information that is the correction with the model that I had in my mind, my projection that I had in my mind from last period. Okay? So it uses all the data. So but recursively, you don't have to do that all at once, and it's updating the state at every point. So your model is calibrated at every point. So a lot of different applications. So I'm gonna stop here,